Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 121, best time to buy and sell stock. After that, we'll go over an actual variant of the original question that Meta asks. They try to obscure the problem by introducing more parameters, but the core of the algorithm remains the same. Okay, without further ado, let's get started. We're given an array of prices where the index represents the ith day. So, looking here, this is the 0th day, 1st day, 2nd day, and so forth. The value on any particular day is the price of the given stock. So, for example, on day 2, the stock is at a price of 4. And on day 5, the stock is at a price of 6, etc., etc. And as you can see, I represent the array in a scatter plot, like so. It'll make the explanation a lot smoother. What we want to do is choose a single day to buy the stock, and then choose a different day in the future to sell that same stock. We're only allowed to do this transaction one time and one time only, and it must be the transaction that yielded the maximum profit. Let's take a look at some quick examples of some transactions. If we chose to buy the stock on the 0th day for a price of 7 and sold it subsequently on the 2nd day for a price of 4, then 4 minus 7 means we actually lost money. Now, it's noted in the problem description that if we cannot achieve any profit, we can just cancel the transaction and carry on with breaking even with a 0. I wish that was how it worked in the real world, but anyway, let's look at another example. If we chose to buy the stock on the 3rd day for a price of 1 and sold it on the very next day, day 4, for a price of 10, then that means that we made a net profit of positive 9. And as it turns out, this is the best transaction that we could have had. We returned the 9 as the answer. Okay, that's great, but how do we actually solve this? The brute force solution is to try every possibility with a nested for loop. We'll have an outer for loop with the pointer I, and for each of these iterations, the day that I points at will be the day that we choose to buy the stock. Here it's 7. Then we can have an inner for loop with pointer j to iterate through the rest of the days in the future and try selling on all those days. Here, namely, that's day 1, 2, 3, 4, and lastly 5. Just saying, you can technically sell on the same day, but why would you do that? You'd always be left with a profit of 0. If you bought the stock for a price of 7 and then sold the stock for the same price of 7, you indeed get the 0. This is all to say that basically we want to start j on the next day after I, so on day 1. Alright, before we try a walkthrough, let's initialize a variable called max profit that represents the most profit so far. We can default it to 0 because we haven't made any transactions yet. Okay, so on the first iteration, j is on day 1. If we had bought it for a price of 7 and sold it for a price of 3, then that means we go into the negative with negative 4. Comparing the two numbers, we'd rather opt to break even with the 0. Remember, that is a thing we can do. Let's move on. On the next iteration of j, we're now on day 2, where we try selling for a price of 4. Our I, remember, is anchored on day 0, so we're still buying for a price of 7. The math tells us that 4 minus 7 still yields a net loss of negative 3. It's a bit better than before, but we still lost money. We rescind the transaction and pretend nothing happened. We stick to our 0. On the next iteration, j is on day 3. We sell the stock for the worst price ever of 1, and buying it for a price of 7 means we lost the most money so far. Comparing it with our max profit, our answer so far remains as 0 still. Finally, on the next iteration, the stock price went up drastically. That's good for us. And indeed, 10 minus the 7 yields a positive 3. That's nice. We made a profit for once. And furthermore, it's greater than our max profit so far of 0. So let's update it to the 3. On the last iteration of j, we sell for a price of 6. And having bought the stock for the 7, let's do the quick math. 6 minus 7 is negative 1. That is lower than our max profit of 3. We don't update that variable and we move on. When j has exhausted all possible sell days, we'll increment our I pointer to day 1 and do it all over again with j on its next day, day 2, to sell on all future days. So this time it'd be day 2, 3, 4, and 5. But let's cut the walkthrough right here. We know better than to solve this with a nested for loop, which results in an n squared time complexity. We can actually find the maximum profit in one pass with a single for loop. But what's the intuition? Let's revisit our brute force solution and try to understand what we did from another perspective. For example's sake, let's hyperfocus on this day, day 4, as the day that we try to sell our stock for a price of 10 in hopes of making money. Now, what were the days when we bought stock to sell on this very day? Well, it was all the days before, right? Our outer for loop I started on the 0th day, where we try to buy it for a price of 7. And then later at another point, I was also on the first day for a buy price of 3, and then the second day for 4, and the third day for 1. So in a way, we're thinking about this in reverse. Looking at the sell point on this day, what was the best day to buy stock to optimize revenue? Well, obviously we want to buy low and sell high, so we'd buy at the minimum price of 1 on day 3. And indeed, 1 is less than the 4, 3, and the 7. Looking at the math, selling it for 10 when we bought it for 1 yielded a max profit of 9, which was the highest profit we could achieve on day 4. Okay, so here's the overall observation. If on any given day that we sell, we wanted the minimum buying price from the days before, then we can think about this the other way around. We can iterate from left to right and keep track of the minimum buying point in a variable perhaps called minimum buying price, which again, when we got to day 4, we observed it to be the price of 1. And if we did that, we can do some quick maths like we did on day 4 on every iteration to see if we made money or not. And if we did, like we did here with the positive 9, we can update the same max profit variable that we had in our brute force solution to the highest profit so far of 9. That's the general idea of the algorithm, at least. Let's go through a full walkthrough. On the initial iteration of our for loop, we're on the 0th day. The first thing we'll do is try to sell on this day. But hold on, we haven't actually bought the stock on a previous day yet. There's no -1 day that exists. Day 0 is literally the first day. Technically, we can buy and sell on the same day, but we wouldn't make anything other than break even. Remember, 7 minus 7 is the 0. This is just a calculation we don't have to make. Therefore, let's make one final adjustment. We'd rather start looping on the first day to start selling and assume we had bought the previous day on the 0th day. Therefore, let's default the minimum buying price to the price on the 0th day. That's the 7. Alright, that makes more sense. Now we can start selling on a day where we had previously bought the stock. With that, we can officially start the walkthrough. Okay, so we're on day 1. We'll do two things. 1, assume that we sold on this day. How much profit did we make? Well, if we had bought it for a minimum buying price of 7, as shown here, then doing the quick maths, we get -4. Comparing that to our break even of 0, -4 is terrible. We act like nothing happened and we do not update our max profit. The second thing we'll do on the current day is we'll update the minimum buying price, but only if we found a cheaper price to buy the stock. And indeed, 3 is less than the 7. Therefore, we'll update this variable to the 3. And to show this visually, so we can follow along a bit easier, let's just denote the minimum price here at the 3. We move on to the next iteration, where I now points at the second day. We repeat our logic. If we sold on this day for a price of 4, how much money did we make? Well, we now buy it for the cheaper buying price of 3. In doing so, will get us +1. That is higher than our max profit so far of the 0. Let's update it to this profit. The last thing we do is check that on day 2, where we currently are, if the price to buy the stock is the cheapest yet. We compare the 4 with the minimum buying price of 3. Remember, that's denoted in this variable here. that 4 is more expensive, we'd rather stick to the 3. After that, I is incremented to day 3. We can already tell we're screwed. If we sell for a price of 1 and had bought it for a price of 3, then that means we lose $2. We compare this with our max profit, and we take the higher value, which is the 1. As always, do we update our minimum buying price? Well, looking at the current day, we have a price of the stock as 1. 1 is lower than 3, so let's update this variable to the 1. Great, let's update our visual as well to denote the new minimum buying price. Okay, on the next iteration, we encounter an amazing price to sell at, 10. It's a good thing we updated our minimum buying price to the cheapest price seen so far, because now if we buy on that day, 10 minus 1 gives us positive 9. That's surely greater than our max profit so far of 1. Let's update it to the positive 9. The last thing we ask is that on day 4, would we rather buy the stock for a price of 10 or the minimum found so far of 1? It's obviously the 1. This variable remains unchanged. Great, now on the last iteration, we sell for a price of 6. Was the minimum buying price? It's the 1 as seen here in our visual. So real quick, 6 minus 1 is 5. Comparing that, 9 is greater, so we keep 9. We move on. We increment I, and we're done with our for loop. In retrospect, our best strategy, given this example, was to buy on day 3 for a price of 1, and then selling it the very next day, day 4, for a price of 10, earning us a net profit of 9. That's what we return. The time complexity is big O(n) because it's a single for loop, and the space complexity is big O(1) because all we had were constant fixed variables, like this one right here and the max profit. That's efficient. Alright, with that said, let's code this up. Just as a quick note, I'm coding this solution in C++, but check out the link in the description below for the solutions in other languages like Python. Okay, so first off, we'll initialize our minimum buying price variable to the price of the 0th day. Remember, we do this because we can only sell stock when we've actually bought the stock. So we'll assume we bought it on the 0th day, and then start selling on the 1st day to see if we make any profit. And if we do make the highest profit yet, we'll update another variable, max profit. We're going to eventually return this variable, so let's write that before I forget. And with that, we can start our for loop where we're going to start on the 1st day. On any given iteration, we're going to do 2 things. First, we'll try to calculate how much profit we made by doing the current price on the current day minus our minimum buying price variable. And if it turns out to be higher than our max profit so far, then we'll update our max profit variable. Secondly, we'll see on the current day if the price of the stock is cheaper than our minimum buying price. And if that's the case, we'll update the minimum buying price to the cheapest option so far. And that is it. Let's get into the variant. At least in my experience, I've almost never seen Meta ask the original LeetCode question. They very much prefer this variant, where instead of 1 array, we're now given 2 arrays, departures and returns, where the values are ticket prices on the ith day. So looking at our example here, we have the 2 vectors, departures and returns. They're guaranteed to have the same length. So if we had pointer I on, say, day 3, then it can safely refer to a return ticket for a price of 2, as well as a departure ticket for a price of 11. We don't have to worry about any out-of-bound access errors. Going back to our problem statement, we have to choose a single day to buy a departure flight and another day in the future to buy a returning flight in such a way that minimizes our cost. Once we found the cheapest round-trip flight, we return the associated minimum cost number. Overall, this variant is different from the previous problem because before we were trying to maximize our profits by subtracting the buy price from the sell price. But here, instead, we're trying to minimize our costs by adding the departure ticket and the return ticket. Alright, so I already explained the thought process to arrive at the optimal big O(n) time complexity in the problem before. I'll do the same thing for the variant here, but I won't go as in-depth. First things first, what's the brute force solution? We can use a nested loop to try all possible round trips. Our outer for loop I starts on the 0th day in our departures vector, and its inner for loop pointer j starts on the day after in the other vector, day 1, which is +1 from 0. Remember, these indices can refer to either vector, but here we'll visually put j underneath the returns vector because that's what we'll be accessing with j, not the departures one. Now, as to why j starts on the first day and not the 0th, again, we cannot depart and return on the same day. That's just this rule right here. It must be in the future. Okay, so we're buying a departure ticket for a price of 4 and buying a return ticket for a price of 6. Instead of subtraction, we'll use addition to figure out what our total cost is. The 4 plus the 6 yields a 10, and by default, this is the cheapest round trip we found so far, simply because it's the only round trip we found. Let's update a minimum cost variable to reflect just that. So we have a minimum cost variable. Next, we increment j to the next day, where we're trying to buy a return flight for a higher price of 10. Our cost comes out to be 4, right here, plus the 10, to get an overall cost of 14, which, needless to say, is more expensive than our minimum cost so far. We're cheap, so we'll opt for our previous found round trip of the 10. On the next iteration, we found a return flight for a price of 2. If we departed on day 0 with a price of 4, which our total cost, 4 plus the 2 is the 6, that's affordable and technically lower than our minimum cost. So let's update it with the 6. So far, flying out on day 0 and flying back on day 3 is our best option. On the last iteration, we increment j to the last day, day 4, where we have a return flight of 9. That, with the 4, yields an overall cost of 13 that exceeds our minimum cost. We won't update that variable. And with that, we've exhausted every return flight when we buy a departure ticket on day 0. Now what we'll do is increment our I pointer to day 1, where we buy a ticket for a price of 3, and we'll reset our nested j pointer to the day after, day 2, and repeat the logic to try every possibility. I'm going to stop the brute force solution right there because this is an n squared time complexity. How can we do better? As we saw before, we can think about our brute force solution in reverse. At some point in our nested loop with j, we would have tried to buy a return ticket, say on day 3, with an associated flight price of 2. What were all the days that we try to buy a departure ticket for this day? Well, looking at our departures, it was all the days before day 3, right? I started on day 0 for a price of 4, and eventually would be incremented to day 1 for a price of 3, and then lastly, day 2 for a price of 5. But anyway, let me ask you this. Which departure cost that, when added with a return flight cost of 2, led to the overall minimum cost? Well, it would have been day 1 for a price of 3. And indeed, 3 plus 2 gives us a low cost of 5. We had tried all the possibilities in our naive approach, but really on any given iteration that we bought a return ticket, like day 3 here for the price of 2, all we needed was the minimum departure cost among all the days before. Therefore, to optimize, we'll iterate left to right and track the minimum departure cost in its own variable. Minimum departure cost is a bit verbose, but at least it's descriptive, like so. Which, if we iterated to day 3, the minimum would have been a departing cost of 3, like we had seen. And also in the same iteration, we'll see if buying a return ticket with that minimum departure cost led to a more inexpensive round trip. And if it did, we'll update a min cost variable to reflect just that, which, remember, the 3 plus the 2 yielded a cost of 5. Okay, so that's the general idea. Let's go through a quick walkthrough now. To kickstart our for loop, we'll initialize the minimum departure cost to day 0's price of 4. And we'll start our I pointer on the first day, day 1. I will repeat myself, we do this because we cannot fly out on day 0 and then fly back on the same day. That's the requirement. All to say, we'll start it on day 1. As a side effect, that does mean we'd never consider a return ticket on day 0 ever, and that's okay. It's just a constraint of the problem. Alright, so on the first iteration of our for loop, if we had bought a minimum departure cost of the 4 and a subsequent return ticket for 6, what is the total cost? 4 plus 6 is 10. Let's compare it with the minimum cost variable so far. But wait, it's not initialized to anything yet. This round trip that we try is technically the cheapest simply because it was the only round trip we've tried. Therefore, we'll initialize our min cost to an arbitrarily high number, say int max, just so that it can be overridden on the very first iteration with that 10. This assumes there cannot be a round trip that amounts to more than 2 billion. I can't think of any flight that expensive, but it's worth clarifying with your interviewer. After that, to end our iteration, the last thing we'll do is update our minimum departure cost if we found a cheaper departure ticket. Remember, I is on index 1, day 1, so we check if a departure ticket of 3 is more cheap than 4. Indeed it is, so let's update the minimum departure cost to the 3. Moving on to the next iteration, we now try to buy a return ticket on day 2 for a price of 10. What is the cheapest departing cost so far? Well, it was the 3. 10 plus 3 is the 13. This current price exceeds the previous deal we found of 10, so we do not update our minimum cost. It remains at 10. As always, we'll potentially then update our minimum departure cost if we found a better price. On day 2 is a price of 5 to depart any better than the 3. No, it's not. We'll stick with flying out on day 1 for the lower 3. We move on the next iteration, we buy a return ticket for a price of 2. That's quite a bargain. If we depart on the cheapest day so far for a price of 3, then 2 plus 3 gives us a cost of 5. We save more money than our previous round trip of 10. Let's update our min cost variable. The last thing we do on day 3 is the departing price of 11, cheaper than what we found of 3. No, it's not. We don't update this variable at all. We move on to the last iteration, where we try a return flight of 9. The cheapest departure cost is still the 3. 9 plus 3 is 12. That's not any cheaper than a round trip that we previously found. We don't update our minimum cost. We update the I once more, and we're done. In the end, the minimum cost we found so far was 5, and that's what we'll return. And just for reference, that meant that we flew out on day 1 for a price of 3, and flew back 2 days later on day 3 for a price of 2. This led to the cheapest option possible of the 5. The time complexity is big O(n) because we only had a single pass, and the space complexity is big O(1). Alright, I hope that made sense. Let's code this up. First off, notice that the signature has changed. We now have the 2 vectors, not just the 1. Next up, we're actually going to demolish all the code from before. Everything technically changes, but ever so slightly. Now, we need 2 variables to ready our loop. One, we have the minimum departure cost, which we had initialized to the 0th day's price. We do this because, recall, we have to fly back in the future. So our earliest option is to depart on the 0th day and return on the 1st day. The other variable we need is the minimum cost. We set that to a very high number. Don't worry, it's guaranteed to be overwritten on the first iteration. We'll eventually return it, so let's just do it now before I forget. Now we're ready for our for loop. Remember, I just said we start looping on the 1st day onwards. Note that I'm choosing to iterate over our departures vector. It doesn't matter which one you iterate over. The pointer I can be referred to both. I just arbitrarily chose the departures one. On any given iteration, we do 2 things. Is the current returns cost plus the minimum departure cost so far cheaper than the min cost variable? If it is, then we'll update that variable like so. And the last thing we'll do in any iteration is ask the question, did we find a cheaper departing cost on the current ith day? And if we did find a smaller cost, then we'll similarly update our minimum departure cost variable. And that's actually it. Not much changes from the original LeetCode problem. It just gets a bit trickier with different parameters. Fantastic. Good luck on your interviews.